Welcome. These are the motion notes for our motion unit, part one, the need for speed. I'm going to go through these notes kind of quickly. If you need to write something down, please pause it. And that way I can keep the video a little bit shorter, it doesn't have those long delays in it. We are going to do parts one, part two, and there's a part three on here that is kind of hidden inside part two, and I'll talk about that when we get there. So part one, the need for speed. The first thing you need to know is distance. The symbol for distance is x. It is not d, as you would think. It is x. And distance measures how far something is. Distance is a length. So you'll notice I bolded and underlined how far, because that's a key words we need to know. And so if you're measuring how far it is from here to your house, from the school to your house, that would be a distance. And the units that we're going to be using for distance are meters, most of the time. But distance can also be measured in feet, miles, inches, kilometers, and so on. There are many more than that, but that's just to give a few. And some things that we use to measure distance. We use a ruler or a measuring tape to measure distance. So you guys are pretty common with distance, or should be pretty familiar. The second variable is t, lowercase t, which stands for time. It does need to be lowercase t because capital T is temperature. So make sure you keep it lowercase. And if distance measures how far something is, time measures how long. How long can you hold your breath? How long does it take you to run the mile? These are times. And the units for time are seconds. And you'll either see it written as an S or an SEC, depending on if it's in the book or written on the board. But other than seconds, you could also measure it in minutes, hours, days, years, decades, centuries, and on and on. And some common things used to measure time. We have stopwatches measure time. And just your everyday clock. The next variable is speed, and speed measures how fast something is going. So if I say how fast are you going, well, that's your speed. And in this class, we're going to be measuring speed in meters per second, but it can also be miles per hour, kilometers per hour. If you're measuring the speed of a snail, it might be inches per minute. It's basically any unit of distance divided by any unit of time. And some things that are fast. We have a cheetah. Cheetahs are fast. And NASCAR, car racing, they're pretty fast too. Velocity. Velocity is a V. And velocity is very similar to speed, but there's a little tiny difference. And so you really need to pay attention to those differences between velocity and speed, because I'm sure that's going to be on the test. Velocity also measures how fast, but it has a direction to it. So velocity is speed and direction. It needs both. And so an example. If I say I'm moving 8 miles per hour, that is a speed. But if I say I'm moving 8 miles per hour east, that would be a velocity. Or 8 miles per hour up, that would be a velocity. Or down, or 8 miles per hour towards the cafeteria, that would also be a velocity. It needs a direction. And sometimes you'll see velocities are negative and velocities are positive. That's also giving it a direction. So if something has a positive velocity, like if you see a number like positive 45 meters per second or negative 13 meters per second, these are velocities because that sign is giving it a direction. And we kind of mentioned before that the positive sign usually means it's going to the right in the positive direction, and the negative sign means it's going to the left or the negative direction. So, so if you see the signs, those signs are also giving it, are also giving you a velocity, a direction. Okay. Units are the same. They're meters per second. And we have an equation. There's our equation. So our equation is V equals delta x over delta t. And I wrote right here these words that delta is this triangle, and it means change. So this right here is pronounced delta, and it means a change in. So this is really measuring a change in distance. And down here, we have delta again. Oh, I'll just draw an arrow this way. So we have a change in distance divided by a change in time. Most of the time, we can just avoid the delta, avoid the triangle. It's really not needed most of the time. When it is needed is if you're not starting from zero. And I kind of explained this in class. If you have say a football field, and you have the 10-yard line and the 20-yard line and the 30 and the 40, you have all these different yard lines. And let's say you start from here, which is the end zone, or the goal, if we're playing soccer, and you get out to here. Well, you would say, okay, I go, that's 20 yards. I count from zero, I go to the 20-yard line, that's 20 yards. So you would just put the 20 right in there at the X. But it gets a little trickier if you are not starting at zero. If you're starting here at the 20 and you go out to the 40, well, what are you going to put in here for X? You put 20? You put 40? You're not starting on either one. So really, you're putting the change in the distance. So the change in the distance would be from 40 minus 20. If you start on the 40-yard line, in on the 40, start on the 20. So you're really going to put the answer in there, which would be 20. So really, it's you're measuring not just the distance, but the change in the distance. Okay, let's look at. Apparently, it's nothing. Let's go to the next slide. Let's look at an example. Moops flies 8 meters in 2 seconds. What is his velocity? And for all these problems, we're going to identify what we know. We know 8 meters, we know 2 seconds, and we're trying to find his velocity. So I'm going to write those down. 8 meters, 2 seconds, what is the velocity? And I'm going to use those units. Meters is a distance, seconds is the time, and the question is asking what is his velocity. So velocity equals delta x over delta t. I substitute, I solve, I put the units, and I box my answer. Easy peasy. All right, the next concept is acceleration. Acceleration, the symbol is A, and acceleration is a change in velocity. So I wrote this 2 ways. I wrote this using English here, and I also wrote it in math right here. So acceleration is a change in velocity. So let's assume I am sitting in my Ferrari at a red light. The light turns green. I floor it. Am I accelerating? Yes, I am accelerating because I am changing speed. I'm going faster. If I travel a couple of blocks and I come across the red light and I slam on the brakes, am I accelerating? Yes, I am accelerating because there is a change in my velocity. I am slowing down. So there is an acceleration, and we would call that acceleration negative. So if I'm slowing down, I would have a negative acceleration. And I'm also accelerating if I go around a corner. So if I'm going 30 miles an hour constantly around a corner, I am accelerating. Even though my speed didn't change, I was constantly going 30, the direction changed. And remember that velocity is speed and direction. So this is a very key thing to know. Well, we said acceleration measures how much velocity is changing every second. And acceleration happens when things speed up, slow down, or change direction. This is highly important. So we're going to definitely highlight all that. Acceleration happens when things speed up, slow down, or change direction. All right, let's look at an example. Yeah, that's not okay. Let's go down. Okay, if I have a graph of distance, not distance, let's redo that. If I have a graph here of time, velocity, and acceleration, and if I start at rest and I'm not moving, and then I'm going to change every second, I'm going to speed up. So I'm at a red light. In 1 second, if I'm moving 8, my acceleration would be 8 because it measures the change in the velocity. If on the second I am going 10, my acceleration would be 2 because the change in the velocity is 2. If in the 3rd second my velocity is 5, my acceleration would be -5. Because once again, I am slowing down, so it is negative. And the difference between 10 and 5, it's -5. And so I'll do one more. If I go up to 20, oops, -5. If I go up to 20, it'll be 15. All right. Equations. For acceleration, we have 2 equations. There they are. And a few terms we need to know. Vf is the final velocity. Vi is our initial or our start velocity, and that is there and there. And so we need to keep that in mind. That's actually what I just said. Vi is the initial velocity, or the velocity of the object at the start. And Vf is the final velocity, or the velocity of the object at the end. Delta x means a change. We already said that. You don't need to write that down again. And there was one more thing that's not on here. Let's write it down. There's 2 things we need to know. If something says at rest, we know our starting speed is 0. And if something says comes to a stop, we know our final velocity is 0. So these are key terms that you have to know to solve these problems. It's basically translating English words from a word problem into mathematical language. So make sure you remember to pull those out. Okay. Let's look at 2 examples and we'll be done with part 1. First example, here's Moops, driving at 40 meters per second. I'm going to need that. Speeds up to 60 meters per second in 4 seconds. What is his acceleration? So I'm going to write that stuff down. I have 40 meters per second, 60 meters per second, 4 seconds, and a question. So meters per second is a velocity. So those are both velocities. Seconds is a time. and I'm trying to find what is the acceleration. So because I have two v's, I'm going to use the equation with two v's, but I need an initial and a final. So I read the problem, I realize I'm starting at 40, and my final is 60. So I would have 60 equals 40 plus a times 4. All right, I want to combine like terms, so I subtract the 40. I get 20 equals a times 4. Divide both sides by 4. And I get a equals 5 meters per second squared. All right, let's look at one more example, and then we'll be done with part 1. Did I write over it? Yep, I wrote over it. Okay. So here's the second example. Meeps is driving at 40 meters per second. Covers 100 meters. I'm going to need that in 2 seconds. What is her acceleration? So I'm going to do the same thing. 40 meters per second, 100 meters, 2 seconds, and a question. That is a velocity. That is a distance, a time, and the question is, what is the acceleration? Because I have that x and an a, I'm going to use this equation. And I'm going to plug in my numbers. 40 times 2, 1/2 a2 squared. 40 times 2 is 80. 2 squared is 4. Half of 4 is 2. Plus 2a. Combine like terms. I get 20 equals 2a. Divide both sides by 2. And we get a equals 10. Awesome. All right, that is going to conclude part 1. Let us now talk about part 2, which is free fall. All right, free fall. The definition is an object falling to the ground under only the force of gravity. So we're talking about no air resistance. So we're talking about gravity only, nothing else pushing on it. So if we have two objects, let's say we have a freshman and we have a feather, and we drop them both off the roof of the gym. In free fall, if there was no air, both the freshman and the feather would hit the ground at the same time. Gravity pulls all things the same. So it doesn't matter if it's a 100-pound freshman or a feather, all things will hit the ground at the same time. That is how gravity works. Gravity just pulls everything the same. And this is because gravity's dumb. So the rate that gravity accelerates all things, the rate that it pulls things down is 9.81 meters per second squared on Earth. And in class, we're going to round this mostly to 10. So if gravity pulls all things the same, freshmen or feathers, why do we see feathers fall more slowly than freshmen? And this is because of air resistance. The air is hitting the feather and slowing the feather down. And if we were able to suck all the air out of the room or of the quad, and we dropped both, then the feather would indeed hit the ground at the same time as the freshman. And there are some videos on YouTube of this very thing happening that we watched in class. The last thing you need to write down is a vacuum. A vacuum is space that is empty of matter. So it has nothing in it. No air, no gas, no water, completely empty. So when we talk about free fall and things falling to the ground, we're talking about them falling in a vacuum. So that there's nothing else affecting them falling, only gravity. All right, so an example. If we have time and velocity and acceleration, and if this is in seconds, meters per second, and meters per second squared. Before we drop them, they are not moving. In 1 second, gravity accelerates things by 10 on Earth. So that means in 1 second, it is now moving 10 meters per second. In the second, gravity is still accelerating things at 10. Guess what gravity does? So now, instead of moving at 10, now the feather or the freshman or the rock or whatever you're dropping would now be falling at 20 meters per second. Same thing's going to happen in the third second. Gravity still pulls down by 10. So now it's falling 30 meters per second. So you can see it's getting faster and faster and faster and faster because gravity is accelerating it by 10 meters per second every second. Air resistance is the friction caused by air, and it slows down the motion of an object. So if you're driving down the freeway, you roll down your windows, you stick your hands out, you can feel the air hitting your hands. And it actually hits them pretty hard. So that force slows things down. And the amount of air resistance depends on the size of the object. Bigger objects hit more air, going to slow them down more. The shape of the object, things that are round typically deflect air better than things that are flat, which is why sports cars and bullets are kind of round shaped. The weight of the object matters. Heavy things generally can avoid air resistance more than light things. Light things have a bigger, are affected more by air resistance. And the texture of the object. Smooth things go through the air easier than furry things. We also have terminal velocity. Terminal velocity is the fastest speed an object can fall caused by air resistance. So terminal velocity, when you drop a feather, it doesn't keep going faster and faster and faster and faster like the last example we just drew. It actually slows down because it hits this terminal velocity caused by air resistance, and it's going to make it stop accelerating. So if we had an example of something falling with air resistance, the graph would look something like this. So we still have our columns with T, V, and A. But here, because terminal velocity is 20, once it hits 20, it can go no faster. So it doesn't even matter if it's in 40 seconds, 90 seconds. It's no longer accelerating. So you'll see that our A's are 0. And it's not speeding up anymore. And once again, this is caused by air resistance. So we have two equations for things falling. And luckily for us, they are the same two equations. If I can click on it. There we go. We have VF equation for how fast something is falling. And we have the delta X equation for how far something is falling. Don't mix them up. Make sure you have them separated in your heads. There's also something else we know. We know that acceleration is caused by gravity. And on Earth, it is 9.81, which is approximately 10. So we can plug this value into our A's. So if you see the keyword fall, you know A equals 10. So that is something very important that we need to look for in our word problems. if we see that, we need to write it down, a equals 10 if something is falling. So that's what gravity speeds it up at. So let's look at some examples. Moops pushes Meeps off a cliff. How fast is she falling? How fast is she falling after 6 seconds? So how fast? If she's falling, I know A is 10, so that falling word. That's because falling told me that. And I have a time of 6 seconds. So I'm going to use this equation for how fast. A is 10, T is 6, and VI is actually going to be 0. And the reason it's 0 is if you watched this scene in super slow motion, as soon as Meeps went off the edge of the cliff, it would look like she was not going down yet. Very slow motion. If you're holding a baseball, and as soon as you drop the baseball in slow motion, it's going to look like it's not moving, and then it's going to start falling. So because it's not moving initially, our VI is 0. So this just turns into 60. Easy peasy. Okay, second example. Moops pushes Meeps off a building. This time, how far does she fall in 6 seconds? It's going to be a different answer, even though they're basically the same numbers. We're trying to find her x. We know A is 10 because of that keyword fall. And we know a time, 6 seconds. So we're going to use this equation for how far. VI is 0, like it was before. So this just goes away. We're left with half of 10 times 36, which is 5 times 36, which is 180 meters. All right. Part 3 of our notes, throwing up. Very short. Throwing up basically says, if you throw something up, gravity slows it down by 10. So on the way up, objects slow down by 10. Because gravity's pushing down 10. On the way up, they slow down by 10. At the top, the velocity is 0, so they slow down, slow down, slow down. At the very top, they stop, so velocity is 0. But very importantly, acceleration is still negative 10. And then on the way down, objects speed up at a rate of 10. So let's draw one final picture, and then we'll be done. We had a picture of me in a dress. If I throw a ball up at 30, in 1 second, because gravity is pushing down by 10, the velocity, it started at 30, it's slowed down, it's now going 20. So you can see, because it's slowing down, our acceleration is negative. It's going to be negative 10. In 2 seconds, it's going to slow down again, another 10. So the acceleration is still negative 10. It's slowing it down by 10. Here at the top, 3rd second. It is not moving. Slow down another 10, went from 10 to 0. Our A is still negative 10 because it slowed down. On the way down, T equals 4 seconds. So it started at 0 at the top, now it's going down. So, oops, not square. acceleration would be 10. In 5 seconds, it's speeding up again, still speeding up. And right before it hits the ground, it is going 30, and it is 10. So some things to note about this. One, the speed I throw it at is the same as the speed it lands. That's important. I'll say it again. The speed we throw it up at is the same as the speed it lands. You'll see the acceleration is always 10. It's negative 10 going up, and it's positive 10 going down, but gravity's always pulling down by 10. It's always changing it by 10. So on the way up, it slows down. The way down, it speeds up. At the top, velocity is 0. We do have an acceleration of negative 10 still. And that basically sums up the notes. That was part 3. Part 3 is very short. Hope you enjoyed the motion notes. I know that was kind of long. It was longer than I expected. If you have any questions, please feel free to ask me. I'll be sure to walk you through them. Or ask a friend, or watch the video again. Thanks for watching.